All right, welcome everybody. My name is Jan Högelheim. I'm at Argonne National Labs, and it is my pleasure to introduce William Moses, Valentin Churavy, and Ludger Paehler, who are going to give us a tutorial on Enzyme, an AD tool that I'm very excited about, and they're going to tell us how to use this to differentiate any LLVM-based language for CPU, GPU, and more. Billy, over to you.
So, hi everyone. As mentioned, I'm going to be giving a tutorial with these lovely folks on both how to use Enzyme and some of the interesting LLVM specific internals that we came across over the implementation. It's not just three of us, but a large team across our national lab, Tom, and more. Begin by giving a little bit of a tutorial into the problems that Enzyme aims to solve, give a little bit of context, types of operations inside of LLVM likes that we need to perform. And we're going to go right into code snippets and then hand it off from there. So to begin, what Enzyme does is it computes derivatives. And as you might remember from your most favorite class in high school or college, derivatives are used to compute the rate of change of a function's output with respect to a given input. Derivatives, and thus their generalizations like gradients, Jacobians, Hessians, and so on, are widely used across science. In machine learning, this is most common in terms of backpropagation for neural networks, as well as Bayesian inference, among others. In the scientific computing community, if you've ever seen a physics equation with some derivatives inside it, that's directly used right there, but it's also used within modeling and other types of simulation. So what's really cool is it turns out that you can use a computer to take a function as an input and then generate another function which computes the derivative of that as an output. So over here on the left, we have this function ReLU3, which says if x is greater than 0, compute x cubed. And we're able to run it through a tool, in this case, using a method known as automatic differentiation to generate the gradient of this. In this case, it's shown on the right of 3x squared if x is greater than 0. And notably, unlike numerical approaches, automatic differentiation can, one, do this without approximation error, and two, compute the derivative of either all inputs or all outputs with a single call, which makes it quite efficient in practice. So there tend to be three different approaches for doing this. The first of which is you would rewrite your code inside of an existing domain-specific language. Examples of these include TensorFlow or PyTorch. And this requires taking that ReLU3 case and rewriting it in its entirety into a language like TensorFlow, shown here on the right. And of course, if the DSL, such as TensorFlow, matches quite well with the types of things that you want to do, this can end up being quite fast, although you still have to do the rewriting. However, if the DSL doesn't quite match, then it may be impossible or quite difficult to perform this rewriting process. The second approach tries to do a little bit less rewriting by using tools inside the language itself to make this a bit easier. So specifically, it's called operator overloading. An example of this in C++ is called adept, and an example inside of Python is called JAX. And what you do is you create differentiable versions of existing language contracts. So as an example here inside of C++, again, we have the same ReLU3, except now we've written it to be templated on the type T, so it can take any type as an input. And now inside of adept here on the right, we'll hand in, instead of a regular double, this differentiable double on the right, and we will store all the instructions inside of the adept stack, which eventually are interpreted in the reverse pass. And this is one of the potential flaws of these types of approaches, in that it often has to be dynamic to be able to store and later interpret those instructions for the computation, which is not necessarily good for performance. And two, these types of approaches don't represent all of the types of language operations. So for instance, JAX may not represent all of linear algebra, and adept may not understand every single type of math instruction, let alone any library. The third approach tries to be the fastest of these. It's called source rewriting. In essence, for instance, here using a tool called Tapanod, we take the entire source code base. In this case, we have that same ReLU3 inside of a source file, and there may be some other header files. It analyzes the entirety of it and then spits out new gradient versions of these source files. So now we have the gradient of myfile.c and the gradient myfile.h. As you can see, there's no interpretation, so it can be quite fast. However, in having a tool which takes in arbitrary C and emits arbitrary C code, it has to re-implement all of the semantics and parsing of a given language, which means that it's difficult to follow along more complex languages, especially the latest in, say, C++. And Morphoid also requires all of the code to be available ahead of time, which makes it somewhat difficult to use with external libraries. Generalizing a bit here, all of those approaches tend to operate in the same way, where you have your original source code that you want to differentiate. You have your tool that works for your given language that takes that language as an input, outputs new code in that same language, and then it runs through the standard compiler pipeline down, in this case, through LLVM and subsequent optimizations. So let's go as to how this works in practice. First, we're going to go ahead and define this function norm, which normalizes a vector in O(n) squared time. So for every input element, we're going to set the corresponding output element to be that element divided by the magnitude. Thus, since magnitude runs in O(n) time, the total runtime here is O(n) squared. Now, a good compiler, especially LLVM, should be able to identify that we don't need to call magnitude once per loop iteration, but perform loop invariant code motion to hoist it outside of the loop, reducing the runtime to simply O(n) rather than O(n) squared. Now, if we were able to perform automatic differentiation after optimization, we would be able to see that the corresponding gradient, which effectively reverses the code, or in this case, you can see it, the sort of mirror it, where we had a magnitude call, iteration 0 through n. Now we have iterations n through 0, and then the corresponding gradient magnitude call outside the loop is also running in O(n) time. But this ordering isn't the way that the traditional compiler pipelines work, or sorry, the traditional AD tools work. They first have to run AD again at the source level. So we have here magnitude without the optimization. We subsequently have the gradient magnitude call in the derivative now inside the loop, remaining at O(n) squared time. However, when we go ahead and try to do that subsequent optimization, we find that we can't hoist the grad mag call outside the loop because it uses a variable defined within the loop, in this case, this local variable dres, leaving it at O(n) squared time. So the key insight from this is that by differentiating after optimization, we can create substantially faster, in this case, asymptotically faster gradients. This was presented in earlier work at NeurIPS in 2020 using a tool called Enzyme, which instead of operating at the source level.
Sorry about that. Resuming now, the Enzyme approach enables us to do a couple of key things. First of all, it enables us to take all of the different types of source languages that go to the LLVM framework and have a single tool that differentiates all of them. But secondly, it enables us to push automatic differentiation after the optimization pipeline, therefore allowing us to have the same sort of benefits that we saw on the micro benchmark earlier. Running on a full benchmark suite for both machine learning and scientific codes, we found that Enzyme is able to achieve a 4.2x speedup over those traditional approaches. We subsequently then attempted to go ahead and tackle GPU and some other parallel automatic differentiation, being that LLVM is not able to only emit CPU code, but also GPU code. And we found that not only were those existing LLVM optimizations able to provide a speedup, but in fact, on the GPU, because of that complex memory hierarchy, novel optimizations for both the GPU and for automatic differentiation are required for the GPU code to run it all. This allows thus Enzyme to be the first reverse mode AD tool for generic GPU programs, and thus can emit derivatives for both AMD and NVIDIA. As mentioned, we chose specifically to operate within the LLVM framework because it has a wide variety of these different frontends, as well as the ability to go to multiple different types of backends. Additionally, it has a large collection of optimizations and analyses which are used heavily within the automatic differentiation process itself. So let's do a quick little source code stare right here, and then we'll do some more in-depth dive in shortly. So we have this same ReLU3 here on the left. The corresponding LLVM for this is shown on the right, where first we do the comparison. If so, compute tau. If not, we have a phi node, and depending on which branch we come from, we'll pick the corresponding value. If we wanted to call this from a high level, we would take this magic call to Enzyme autodiff, with as the first argument the corresponding function we want to differentiate, in this case ReLU, and then the argument we want to differentiate with respect to. Enzyme begins by running a couple of different analyses. The first of this is called activity analysis, in which it deduces which of the function arguments and instructions are necessary or impact the overall computation of the derivative. Here, we find that the argument x, the call to tau, the c, and the return instructions all can impact the derivative computation. From here, we go ahead and allocate and zero what's referred to as shadow memory, or equivalently, the location that the derivative or gradient is going to be computed inside of, for all of those active values. Then for each of the instructions which could impact that derivative computation, we're going to compute what are referred to as the adjoints, which effectively propagate the derivative up from its outputs to its users. In this case right here, if we want to compute the adjoints for the tau instructions of x cubed, we'd find that the corresponding thing to do is propagate up 3 times x squared. Doing a little more optimization on this, we find something that looks quite nice. And if we were to retranslate this back up to C code, it looks effectively like the optimal handwritten gradient. And if you want to try this out yourself real quick, we have a compiler Explorer instance here. If you go to enzyme.mit.edu/explorer, you can type in this precise code and then go for it. So without any further ado, let's start writing derivative codes of our own and see what they look like. So I'm going to go ahead and now share my terminal really quick. So if anyone wants to follow along this, we have a Git repo at github.com/wsmoses/enzyme tutorial. So if you want to go ahead and download it for yourself, you can do git clone https github.com/wsmoses/enzyme-tutorial. We have it set up with Docker containers as a way to run it. Alternatively, we also have homebrew packages, so you can go ahead and follow along however you see fit. All of this is on GitHub and will also be available after the talk. Since I already have this downloaded, I'm going to not download it a second time. So let's go ahead and write our first derivative. So let's look at a couple of things real quick. I have a make file, and I also have this square.c function. So if we look at the square.c function, which is popping up, there we go. So we have this function we want to differentiate square, does exactly what you expect, returns x squared. The way to call enzyme is you have this magic function enzyme autodiff, which again takes as the first argument to it the function you want to differentiate, and then any corresponding arguments. Now, the actual function name here doesn't quite matter, so long as it contains enzyme autodiff, it would be fine. I could rename this to enzyme autodiff 2345 or whatever name manglings you like. Since we're in C, I'm just going to use var arg to make it a little bit easier on myself, and it will return the derivative of any of the variables that are effectively floating point as initial arguments. Any data that's inside of pointers or memory, you'll pass in a second version of it, which we'll see so in a second. Again, we go ahead and we just want to call to get the derivative of the square function. So we call enzyme autodiff on square. It will return us the corresponding gradient, and we're going to go print out that the gradient of the corresponding input is the respective output that we want. We take a quick look at our make file right here. First, we have this Docker setup, so you can use the all pre-built versions of it. I call Clang. I can say, okay, with some special flags, go load the plugin for Enzyme, and then output the corresponding file. Then I'm going to run the corresponding file on, in this case, 3.14 as the input. So if we go ahead and do make run square, it will first build for us, and then it will run it. We find out indeed the gradient of square of pi roughly is tau, or 6.28. Excellent. Let's do a little bit more of a deep dive. So we talked about that normalized example earlier. Let's see how it actually works in practice. So if we go to norm.c real quick, we have that same magnitude function. We have the normalized function. We have 2 inputs and 2 outputs. So notably, since we have a pointer as an input, we need to have this notion of enzyme duplicated, which says we have the original input, and this is the location where all the gradients of those inputs are correspondingly going to be placed. So first, we're just going to do, we're going to compute the regular runtime of the function without differentiation. Then we're going to compute the total time with differentiation. And specifically, we're going to go play with this with both the derivative done before optimization and the derivative done after optimization. So if we take a look at this make file right here, this is not the way that one should go ahead and do this normally. You should always do it after optimization as default. But by saying we take the original code, we produce LLVM for it in this unopt.ll, and then we first run enzyme, then O2 to produce enzyme O2.ll. We also have a second version that does O2, then enzyme, producing O2 enzyme.ll, and then we can go ahead and run it. So if we wanted to go ahead and do make run enzyme O2, make run norm enzyme O2. It'll first build the corresponding one that we want, and you see that the regular runtime for normalize is quite quick, and the gradient normalize is still quick, but not quite as quick. Let's see what happens when we run this the other way. So we do O2, then enzyme. So we see here that the gradient is similar runtime to the original function, and thus quite a bit faster than the 0.002 we saw earlier, as we would have expected. Diving up a little bit, we can talk some more fun about the internals. I do need to open it. We just go into the folder. So let's look at this lovely file here, dot, which what it does is it takes the dot product of A and B. We add this extra value C. And the important thing that we want to come across here is, again, we have the corresponding inputs and outputs. So we have, again, A and B, and we have the location gradient A and gradient B, which will store the corresponding gradient. If we were to just pass these arguments in by default, it will compute the derivative of all of our inputs. However, we might know from our application use case, we don't need the derivative of all of our inputs. So for instance, we can say, you know, I don't need the derivative of A. You can tell Enzyme this by passing in first a constant Enzyme const, which says we don't care about the derivative of this. You don't correspondingly need to have a derivative location following it. We're still going to compute the derivative of B. And then finally for C, because it's a floating point input, the gradient will be passed through the return here, thus the Enzyme out. And again, that integer here, n, saying that's the number of elements in the array. That's also, we're not just going to differentiate with respect to that, so it's a constant. So then if we run this, and the way for doing this is the default, which is the easy way to do so. Again, you call Clang, you give it the inputs, you use those flags I mentioned earlier, you just add on to Clang and it will produce you your output directly. And you can go ahead and run it and see how this works in practice. So we can do make run dot. So we see that the first version of this runs in 0.6 seconds, and we see that it computes indeed the derivative of A and the derivative of B, and that output derivative C. But if we say we don't actually need the derivative of A, the runtime here is now 0.03, so roughly half the time, as would make sense. And we're not actually computing the derivative of A. It's set as 0, which is what we had before we passed it in. So if we don't want the derivative of anything, we can inform that activity analysis we saw earlier, which deduces which instructions and values contribute to it, and tell it we don't actually need that part of the computation. Let's do something a little bit more fun. So Enzyme has built in a number of default derivatives for all the common math functions and all the common instructions you'd see at an LLVM level. However, there are still some types of things that you can do, which would quickly end up in code that doesn't make sense to be differentiated. So let's look at this fast inverse square root. So this is a famous code from, I think the code is Doom, in which doing these magic bit hacks will compute approximately 1 over the square root of this input number x. And it's not necessarily obvious how to differentiate through all of these bit hacks. And we'll see shortly that Enzyme will come up with a hi, we can't deduce the type of this particular instruction right here. So the question is what to do with it. Let's go ahead and see exactly how that happens in practice. We can also here take a quick look at our make file, and we'll see that we have 2 versions of it. So let's do the version that would just be the naive version. So we're going to do make square root custom dot, no custom dot o. And we do indeed see that Enzyme tells us, hey, I can't actually handle this. I have an error. The way we remedy this in practice is we can say, okay, the custom derivative, as one way to do this, of this inverse square root is a corresponding other set of instructions that computes the inverse square root. You could also remedy this by telling it how to differentiate through the bit hack, but being able to specify custom derivatives is also useful if, for instance, you have some other high-level domain information that may not otherwise be obvious to the differentiation process. So here we say that the corresponding custom derivative of that input function, q reverse square root, we register it by making a magic global that contains the string Enzyme register gradient. The first part of this tuple is the function with the custom derivative. Then we have the forward path. So when we first run the program originally, before doing that reversal computation, this will be run in place of it. In this case, since we don't actually need to store anything, we can just have this be completely empty. And then the corresponding gradient of that input problem. So since we knew that originally this computed, x to the minus 1/2, we want to actually return minus 1/2 x to the minus 3/2 times, in this case, the gradient output. So that's precisely what we go ahead and compute. If we want to enable this, I've set this up with a if-def conditional. So now if we look at our makefile, we say, oh, go add that little custom derivative that I'd written right there so that we can compile it with make run inverse square root dash custom. And this time it actually succeeds at running it, and we indeed get the correct gradient output. So if we have this sub function, which is perhaps used in a larger program, for instance, used in this part of the program here, we can specify the custom derivative of any part of our code correspondingly. Another cute little thing of note, Enzyme has a bunch of optimizations internally for being able to figure out the fastest way to compute the derivative of your code. One of the most important of these is it may need to preserve certain values from the original run of the program, again referred to as the forward path, for the computation of the reverse of that program, which computes the gradient. So if we look at this program here, cache.c, we see we take an input array, we compute the sum squared of all of these elements, then we store the sum squared of all of those elements into some output pointer. Now, without any additional information, LLVM has to assume that the input pointer and the output pointer touch the same memory. So that's when we're storing this output here, we might have overwritten into one of the locations inside the input. Now, since we're computing the square of the input, the corresponding derivative of the square, as we saw earlier, is 2 times that input. But if we've overwritten that input in right here by doing the store to output, we're going to have to store or preserve in a cache all of the input elements to compute that corresponding derivative. That would actually just look like something like this, where we'd say, double star cache equals new double of, in this case, say n. I'm doing pseudocode here for ease to exemplify what Enzyme actually does. When it does this sort of computation right here, we say cache of I equals n of I, and then when it actually goes ahead and performs the derivative, we would end up using the cached version rather than simply calling in, because it, again, may have been overwritten. We have a second version of this, which explicitly marks the input and the output variables as restrict, and thus they don't overwrite each other. And we'll see shortly how this can be made a tiny bit faster. So let's look at these two versions of this again. So if we see inside of our makefile, we have both the aliasing version and the no alias version. And I've added this extra flag here, rpath equals enzyme. What this path specifies is if there's any performance characteristics that may make it slow or other things that are useful to know, it will provide for the user source line location why this may occur. So if we run make cache alias.o, we'll see here that it says, hey, this load inside of n of I may be overwritten, and it's necessary for the reverse path. So Enzyme has to go ahead and cache it. If we run the corresponding program, you see that it runs in this case, 0.17 seconds. We can now do the alternate version, where here it again compiles the code, but now this time, even with that analysis, it doesn't say that it potentially needs to preserve some values. And we see that it runs in 0.04 seconds, which is a lot faster than the version started. The last of these little cases that I'll go over before handing it over to Ludger, who will talk about some of the aspects of parallelism and a bit of a deep dive, is how Enzyme's able to work with multi-source code bases or libraries that you may want to compile. So here, if we look at multisource.c, I have this magical library called myblas, which contains the definitions of myblas c dot and myblas complex absolute value, takes in these particular arrays of 2 complex numbers and does the corresponding operations. But of course, these definitions are not available in the source file. So what an AG tool would have to do here is it might get stuck because it can't see the definitions of all of these things. But happily, Enzyme, by being baked into LLVM, can run the automatic differentiation process anytime in the LLVM stack. So if we take a quick look at our makefile, what we can do is we can say enable link time optimization. Then we can run the Enzyme differentiation process at link time when all of the definitions of both our libraries and our multiple source pieces are available. There's alternate ways to do this as well, using embedded bitcode or, again, similarly custom derivatives. And this is just one way to go ahead and do so. So I'll do a quick make clean. You make lib.exe. So build all of these different pieces, run the library, and indeed, we compute the derivative as expected. Now I'm going to hand it over to my colleague Ludger to talk about parallelism.
Hey, Roy. I'll quickly talk a bit more about the parallelism that we expose in be able to handle in Enzyme these days. So there are multiple types of parallelism that we're focused on. So recently we've started adding in MPI and OpenMP features. Before that, we first started looking at CUDA code, which, if you want to deep dive into the specific of that, I'd recommend there's a PDF and also recording of the SC session of where William presented the work on the idea of CUDA kernels and the techniques behind it. So if we jump into CUDA, what is the main constraint factor that we have to consider about if you want to use CUDA today? Then the first factor is that you have to work with custom LLVM, which basically needs to be source built and have MVPTX enabled. And then you can start pointing at your CUDA installation. And if we, for example, take a look at what we look at here. So what do we have here? We have to stay, basically have our main data on the device, and we send our data there with explicit the CUDA mem copies to the host. And through all of this, Enzyme is able to differentiate through it. The big point here is that basically right now we can only do a single GPU, and in a way you are at the hand of the libmath function of CUDA. But other than that, Enzyme is able to differentiate through it as you would expect and produce gradients for those. But if you want to move to a more sophisticated gradient, then what you will have to do is you have to basically add custom gradients, which are explained on the webpage, which go a bit beyond the tutorial right now here. Other than that, so the only real changes in the code here is the call to Enzyme autodiff, where we have to use the dupe and basically to signify where we want to differentiate, and that's basically it if you want to use it. So let's quickly go into, so the disclaimer here often is also that in the innate way that Enzyme works, you basically, so for just specifically pronounced for MPI, is that the MPI functionality you use has to be implemented in Enzyme's, sorry, yeah, has to be present in Enzyme's autodiff in Agile generator. So what we have to consider here is that basically that MPI is a giant standard. So what we did, we basically implemented a subset based on some simulation code, which is covered by us. So what we have here is, let's get it up. So these are all the primitives we cover right now. Is basic. So if it, if you have a request for a primitive which is not covered right now, which we'll find out, then we'll be able to patch it up But basically, those are the primitives which are covered right now and which will work as the way you expect. On OpenMP land, what we currently cover is we can do normal parallel loops, OMP parallel, with the way you would expect, the OMP parallel default. You can do OMP, the same thing goes for OMP parallel 4. Which again is as you would expect. Basically, you only have the OMP parallel 4 region in your code, and then Enzyme autodiff does the rest for you. The same also goes for first private and also with no unroll. So that's it from my side. I would hand it over to Valentin.
Hello, my name is Valentin Churavy. I work on the Julia integration with Enzyme. And just as a quick taster, Julia is a high-level dynamic language that targets LLVM, and one of my favorite features of it is the ability to introspect very concisely functions. And so here I have a little sum function, and I just want to see directly the LLVM code, and so I can use the @LLVM macro, and I then get, with including debug information, etc., all of the code that Julia lowers directly to. And that kind of reflection is very helpful when you actually then go out and develop LLVM code. The notebook that I'm using is available in the tutorial Git. So if you have time, I encourage you to just go through it a little bit. As Billy mentioned, there are these notions of activity, and instead of them being magic constants in C, they are actual struct types, and you can directly construct them. One thing to note is the default value is always const. So if I try to differentiate the square function without annotating any value, you will see that I will not get any gradient information. What I need to do is I need to pass it in as active, and only then we will differentiate. In contrast to other Julia AD tools, Enzyme can handle mutating functions, and since we're running a little bit tight in time, let's go to the thing I think that people will be interested in quite is the ability to get the LLVM code directly, similar to the compiler explorer instance, but for also much more complicated examples through the Enzyme compiler bindings. And so here, if I'm looking at the cube function and I want to get the code that Enzyme will synthesize, I can use the Enzyme code LLVM function and then go through and see how did Enzyme actually create, what gradient did Enzyme actually synthesize. For the Julia folks as well, the fact that we are able to differentiate through control flow with data dependencies and without data dependencies is quite novel in contrast to other AD tools in Julia. And we are fast, right? So in Julia, if you want to differentiate for such a forward function, forward diff is normally the best choice, but Enzyme, in contrast, is roughly twice as fast. Okay, so skipping a couple of things. As Ludger mentioned, Enzyme is capable of differentiating through parallelism, and we added support very recently to also differentiate to Julia-based parallelism. So we integrate with Julia's GPU compiler, and we support CUDA.gl and AMD GPU.gl codes, but we also support native Julia tasks. And so this is very recent. It's still in the beta phase, and we are working on stabilizing that feature. If you're interested in bringing another language to Enzyme, you provide two ways of doing it. One way is to have the Enzyme path, which is a normal LLVM path that you can integrate into your pipeline. And another way of going about it is the Enzyme C API. And so this is how we do it in Julia. We obtain the LLVM IR from the Julia compiler. We run an early set of optimizations. Then we provide type information to Enzyme. And so we use the Julia type information that we have, the knowledge, what is a floating point number, what's not a floating point number, propagate that information all the way down to Enzyme. We register custom adjoints for runtime function. And as an example, that's how our thread support works. We're having a custom forward and a reverse mode path definition for what it means to create a task, to schedule a task, etc. Then you run Enzyme create augmented primal or Enzyme create primal and gradient, and that will synthesize the gradients. And then you have an LLVM module at hand that contains the gradient definition. And now you have the challenge of executing it. And so in Julia, or in Enzyme.jl particularly, we use the org-jit interface to link and compile the code. And then the last very bit is very dependent on your language. You need to be able to call it from the user program. The ABI can be finicky to get right. Let's stop at this point, and I will turn it over to Jan for a question and answer.
All right, so thank you everyone for this talk, and thanks Valentin for catching up a little bit on time. So I do want to say before we start with the Q&A that the speakers are happy to answer questions on the Enzyme mailing list, which is on the Enzyme website, or on Pigeonhole even after the end of this Q&A if there are any more questions. So let's dive straight into the first question that we got. And while we do that, please feel free to post more questions on Pigeonhole. So here we have a question about, does Enzyme currently require thick LTO and wouldn't work with thin LTO?
So the example of the multi-source that we did was one way to achieve multi-source AD. The sort of logistically easier, rather than going through the full LTO approach, is to just say, I want to compile the individual LLVM components of all of these, even without LTO. And then you could say LLVM link them all together, and then run differentiation on the entire piece without even running the link time optimization between them. Alternatively, as well, to running with LTO, you could use what's referred to as embedded bitcode, which when it compiles the library, also provides the LLVM bitcode for the functions alongside it. Enzyme doesn't actually need the entire thing in one module, like doing the optimization in full LTO. It just needs to potentially see the definitions of functions to be able to produce the gradient. And the thin LTO was an easy way for our test case to be able to show you how that can be done.
Thank you. And then since I don't see any other questions, I'm just going to pose a more sort of open-ended future question. So where do you want to go next? And do you see any languages that you won't be able to support with this approach, even though they are supported by LLVM? What are your future challenges and directions?
Sure. So a couple of future directions that are particularly interesting is, so we've been recently doing a fair attack on different types of parallelism, such as the GPU, CPU, and distributed parallelism through MPI. The next thing that we want to sort of attack is combining scheduling with differentiation. So for all those familiar with Poly, we want to see if we can sort of combine the optimizations from there with differentiation for faster code. As for languages that are supported by LLVM and not this, they should be able to simply be done. The one thing is we might need some additional analyses or additional metadata, which is just a matter of making sure that the front end nicely talks to the internals.
Yeah, and the example of Julia shows that you can take a dynamic programming language with garbage collection and very different semantics and also differentiate through it as well.
Right, thank you very much. And I think that's all we got time for today. So thank you, speakers. That was a great talk. And thank you, audience, for showing up. And feel free to continue to ask questions if there are any.